Okay, welcome everybody. Nice to see everybody. So today we are gonna just continue working on the sheet of introduction to direct proof that we started last time. So we've talked about chapter 2, that was all the stuff with logic. Chapter 4 is direct proof. And then after we kind of finish up talking about direct proof, we're going to take a jump back to chapter 1 and talk about some really basics of set theory. So we may start some of the set theory today. That's what your reading quiz will be for Monday. Will be more on the set theory, and then we'll talk about proofs for set theory, direct proof with set theory on in Monday's class. So definitely, hopefully you started thinking about the homework, which is due for on Monday. But if you have any questions, I've got office hours tomorrow, so happy to help. Okay, so yeah, we were working with all of this last time. So we did one together, and then in groups, I had you think about question number 2. So by my record keeping, we're at question number 3 on these. So I want to go through one together just to give you a chance to ask some questions. And then I want to spend a bunch of time today having you guys work on some of these in your groups, and then we'll come back and share. So I'm going to break us up into groups a little bit, assign each group one of these to really focus on, and then when we come back together, the groups will present their proofs to the class. Okay, so kind of the gist of direct proof is as follows. We're going to use this when we're trying to prove conditional statements. If P, then Q. And so certainly the statement might not always be stated so clearly as a conditional. So we did some work already thinking about how we can re-express things with conditional statements. So you first want to be able to recognize what is P, what is Q. And then the textbook does an interesting job of explaining how to do these. I think they say direct proof is really, really easy. The first sentence is suppose P is true, and your last sentence is going to be therefore Q is true, and then you just got to fill in the blanks. Okay, but they left out the part that, you know, the tricky part is what happens in between those two sentences. So that's what we'll work on today. But it is nice that you have at least, this is my starting point, and I know when I get to this point, I'm done. So let's take a look at the third one, which is, okay, we've got two integers, x and y. X is even if and only if x plus 4y is even. And I just want to remind you that we did define things such as even and odd and parity last time. So we're going to refer to those definitions that we used last time. Okay, so let's see. X is even if and only if x plus 4y is even. Okay, so let's prove that over here. Oh, that's not what it says. Oops. Okay, so okay, so that's what we're trying to prove here. And we're assuming that x and y are integers, and when we're talking about odd and even, that those are things that just apply to integers. So one difference here is this is an if and only if statement. So this is like a biconditional statement. And sometimes in math, you might see if and only if abbreviated with IFF or the biconditional symbol. So when we have a biconditional statement, remember, first of all, we've got two things here, P and Q. So in this case, the first thing is the statement x is even. And the other statement is x plus 4y is even. And so we certainly can go ahead and try and prove that. But if we're proving an if and only if statement, what else would we need to show?
We'd have to show that P and Q are interchangeable.
Yeah, so that's right. So these things should be equivalent. So we would need to show if P is true, then Q is true. And what else?
If Q is true,
then
P is Q. True.
That's right. So we need to go in both directions here. So this is typically called the forward direction, and this is typically called the reverse direction. So we need to prove this and that. So we need to show that both of those things are going to be true if we want to prove an if and only if. So maybe I'll do the forward direction. We can do the forward direction together. And then when we break up into groups, I'll have one of the groups think about the reverse direction of this proof. So let's take a shot at this direction at least. So our proof is going to start with, suppose P is true. So that's where we would start. And we're going to do some stuff, and eventually and ideally at the end, we're going to get to that point. So any questions about at least the setup so far, how we identify P and Q, and why we're starting with X is even and going towards X plus 4Y is even? Okay, anybody have a suggestion then about how we can get this proof started?
Substitute or do X equals 2A.
Yep. So then we can say, okay, so if X is even, then by definition, we know that X is equal to 2A for some integer A. So basically, we're just restating X is even, right? Maybe using the definition. And sometimes it helps. You don't necessarily need to do this, but it might help to just think about, in the end, if I want to show that X plus 4Y is even, right? Well, then what we're hoping to show is that X plus 4Y can be written as 2 times an integer. So that maybe you can keep that on the side and saying, okay, that's going to be like my second to last line, essentially. Okay, good. So any suggestions about where we can go after we identify that X is equal to 2A?
Plug 2A in for X, and then.
Sorry, I think someone was talking. I'm sorry.
I said plug 2A in for X, and then pull out the 2.
Yeah. So great. So now we can take that 2A and plug it in for the X down here. Okay, so that would mean that X plus 4Y, therefore we can write as 2A plus 4Y, and then we can factor out a 2. And that's basically it at this point. So then we can say, okay, well, since okay, maybe it's just worth pointing out that when we add, bunch, and multiply integers together, we're going to get an integer back. So the integer here is actually A plus 2Y. Therefore, x plus 4y is even, right? That would do it. Okay, any questions? So like in theory, you really should start from the top and try and work your way down. But sometimes if you kind of get stuck coming down, it's useful to think down to the bottom and then, you know, think about what is it that you would want to show, and you can try and work your way up a little bit and join those arguments together. Okay, so if there aren't any questions, then let's get to work on some of these problems. So let's split us up into breakout rooms. And okay, so I can see them, you can't see them yet. So I'm just gonna divvy up the problems like so. So one group is gonna be Heidi, Molly, Yiwei, and Yuzhuan. So for that group, Heidi, Molly, Yiwei, Yuzhuan, you are gonna do the reverse direction of what we just did. So you're gonna do reverse direction of 3. Alex, Brandon, Yarberry, John, and Zara, you will be working on question 4. And Dylan, Giselle, Kaden, you'll be working on question 5. Lindsay, Basi, Victoria, and Wilfred, you are working on question 6. And then that would leave Faye and Stephanie and Yukian. We're working on number 9. But does that make, did everyone catch their name? If you didn't hear your name and what problem you're working on, just let me know. So for each of you, I'd like you to start with the one that was assigned to your group, and then move on to the other ones in whatever order you feel appropriate. And Nat and I will be circulating in just to see how the progress is going. Any questions? Okay, I will split everybody up. Nat, do you mind just hanging out for a minute or so after everyone shoots off? Okay, good luck, everyone. Okay, welcome back, everyone. Great, so let's kind of summarize what you guys were talking about in your group. So we'll kind of take it question by question, and whatever group was in charge of that one can take the mic, and maybe I'll be the secretary. I'll take notes so that we have all of these solutions kind of organized in one place. So let's start with the reverse direction of question 3 that we kind of started thinking about before we broke up into rooms. So the group that did the reverse direction, does somebody mind narrating us through that proof? And I'll take some notes, and then we can see if the class has any questions.
Hi.
Yeah.
Okay, I'll go for it.
Okay.
So since we swapped it, we start with suppose x plus 4y is even.
Mm-hmm.
And then if x plus 4y is even, then x plus 4y is equal to 2a for some integer a, because we're basically restating that it's even.
Mm-hmm.
And then what we did was we moved the 4y to the other side. So x equals 2a minus 4y.
Mm-hmm.
And then we factored out a 2 on that side. So x equals 2 multiplied by a minus 2y. And then since a and 2y are integers, we see that x plus 4y equals 2 times a minus 2y is an even number.
Yep.
Yeah, equals 2b. And then therefore x is even.
Yep, perfect, great.
Props to my group.
Yeah, good job. And so then we prove the forward direction together. That would give us the reverse direction. So then we see that these things are interchangeably. They're actually the same. Saying that x is even is the same thing as saying x plus 4y is even.
Thank you.
Yep, thank you. Any questions about their proof? Did any groups have another really exciting way of doing this one that they want to share? Okay. So then number 4 was if x and y have, and here I'm not going to write every time x and y are integers. That's going to be the case for all of these. So integers x and y have the same parity, then x plus y is even. So who was in, which group was doing this one? You guys want to narrate our way through this proof?
Sure.
Yeah, go ahead, Brandon.
All right. So suppose x and y have the same parity.
Mhm.
And we did this in 2 cases.
Okay.
That means that x equals 2a for some integer a.
Okay,
And
I'm gonna, just to make a little point here, that this came up in some of the proofs and not in others, in that this is a very common sort of proof where we want to break things down into cases. And so it's going to be useful maybe just to indicate how many cases we are and list them out. So the point here is that there's 2 ways x and y can have the same parity, and that might affect the way that the algebra goes in proving this. So we could say, let's let case 1 be, which did you do first, Brandon?
Even. Both were
Okay.
even parity.
So let's say x and y are both even. Okay.
All right. So x equals 2a for some integer a.
Mhm.
And y equals 2b for some integer b.
Okay.
So x plus y equals 2a plus 2b. You can factor a 2 out, so that equals 2 quantity a plus b. A plus b can be set to equal c, an integer. Therefore, x plus y equals 2c, which is even parity.
Yep. Any questions about that case? Okay, and then we've got a second case, which would be what?
That was both x and y are odd.
Okay.
So x equals 2a plus 1 and y equals 2b plus 1 for integers, a and b.
Mm-hmm.
X plus y equals 2a plus 1 plus 2b plus 1, which can be added together into 2a plus 2b plus 2, which you can then factor the 2 out. So 2 times the quantity a plus b plus 1. A plus b plus 1 can be set to equal d, another integer. Therefore, x plus y equals 2d. Therefore, x plus y is even.
Yep. Yeah, so we've got x plus y is equal to 2 times a plus b plus 1. That is some integer. So since we've got that written as 2 times an integer, that's right. Do that. Great, thank you. Any questions from the other groups? Okay, Group 5, or not group 5, but question 5. Does that group mind taking the mic?
I suppose I can do that.
Okay.
So ours was another one with cases.
Yes. Mm-hmm.
So for our initial assumption, we said that P is that, for our first case, we said that P is going to be X is even.
Mm-hmm.
And for our Q for this case, it's going to be that X squared is even as well.
Okay.
And so the way we prove that is by we put 2a is the equivalent of x.
Okay, yeah. So let me, that's right. So this is going to be a cases sort of proof. And one thing I just want to say, which is great that this group thought about, is this is not, at least very clearly, an if-then statement, at least by the way that it's stated in English. So it is useful to maybe think about this as saying, we really have two if statements. If x is even, then x squared is even. And we also have if x is odd, then we would want to show that x squared has the same parity as odd. So it's kind of like two if-then statements. I think that's what you were saying, right, Caden?
Yes.
Okay, great. So yeah, so let's say case 1, we can write it like this. X is even. All right, back to you, Caden.
So we substituted 2a for x.
Mm-hmm.
And then we substituted our 2a in the place of x in our x squared.
And I guess I should be a little more careful here. Okay, so we know that since x is even, x is equal to 2a for some integer a. So therefore, x squared is going to equal, I'm caught up now.
Yes.
Yeah.
So yeah, so then we factored it out and got 4a squared. And we were able to take the factor out of 2. And so we had 2a squared, and that shows that our equation is even because it would be 2a squared is the equivalent of an integer. So we have 2 times an integer is equal to x squared, which is even. And so then for case 2, we followed...
Yeah, sorry, I'm going to pause you for a second.
Oh, cool.
Any questions? Okay, you're doing a good job. Unpause.
Cool. So for case 2, we follow a similar format, starting with x is odd. And so then we supplemented x for 2a plus 1, where a is an integer. And so then we supplemented 2a plus 1 in place of our x into our equation again. And so we had 2a plus 1 squared. And when that squares out, you get 4x squared, or 4a squared, sorry, plus 2a plus 1.
I think you got a little algebra error there.
Yeah, it's, sorry, it is 4a plus 1.
Yeah.
And then we could factor a 2 out of the first two parts. So we factored a 2 out of the 4a squared plus 4a, which then leaves you with, you have, if with a being an integer, that means that 2a squared plus 2a is an integer, which leaves you with 2 times an integer plus 1, which shows that x squared is odd.
Yep. So we've just written that x squared is equal to 2 times an integer plus 1. So x squared has the same parity as x. Questions?
I have a quick question.
Yeah.
Okay, so for the end of the proof, you usually have to write like therefore Q is true. If there's two cases, do we have to write therefore like the parity is always the same for both cases?
So you could, yeah, so at this point, case one, we said, okay, now I can see that x, if x is even, then we see x squared is even, so they have the same parity. And then we do it down here. So yeah, it might be nice before we just say done to just summarize what happened in those two cases. That's not a bad idea. So like you could add a little line over here for the reader to say, since we showed if x is even, x squared is even, and if x is odd, x squared is odd, therefore x and x squared have the same parity.
Okay, so should we do that at the end of like all proofs if we have more than one case?
I think that when you're first starting writing proofs, it's better to err on the side of providing more detail than not enough.
Okay,
Yeah.
thank you.
So I think that having a little sentence to just tie it together is a good idea. Yeah.
Okay, thank you so much.
Yep. Anything else? Okay, then let's see. 6, this was, yeah, that's written over here. Which the group that was doing 6, mind taking control?
I'll go ahead and do it.
All right, that's the spirit. Thank you.
So ours was let x and y be integers for all x cubed minus x is even. To start, we had p as x is an integer. And q is x cubed minus x is even.
Okay. Sounds good.
And then we assumed p was q, so suppose x is an integer. If x is an integer, then by definition we said that x, well, we went around it 2 cases as well.
Okay.
So if you want to go case by case, we'll do that.
Okay, so x is an integer. Case 1.
Okay, so the first case was x is equal to 2a, signifying the even numbers, because we basically split integers into 2, even and odd.
Yeah, right. So we'll say x is even, so therefore x is equal to 2a for some integer a.
And then when we plugged 2a in for x, in x cubed minus x, we simplified and got we simplified and got 2 times 4a cubed minus, well, that. I'll read that all out if you would like.
Yeah, so go ahead. So after you simplified this, you got
2 times 4a cubed minus a. Okay, and then that proved that we would get an even number out of that.
Yep. Okay, so this shows that x cubed minus x is even if we start with x being even. Got it.
And then our second case was x is equal to 2a plus 1.
Okay, yeah, and it might just be good to state in words that now we're assuming if x is odd.
Oh, yeah. I said signifying odd numbers. The way I did is I just did your steps. I did 1. I identified P and Q. 2, suppose x is an integer 3. I proved both. I said by definition 2a signifying even odd numbers and 2a plus 1 signifying odd numbers. I mean even numbers and odd numbers. And then I did all of it, and then 4 I explained everything like all together instead of doing it case by case.
Okay. Yeah, so I think that whenever you're breaking this down into what if x is even or what if x is odd, I think it's good to indicate to the reader that like we're breaking this down into cases, because it just might help someone figure out what's going on.
Okay.
Yeah, so it's very, very common that when you're doing proof by cases, you just label them case 1, case 2, case 3. You might have more than 2 cases.
Okay, and then you just explain.
Yeah, if you wind up having like 20 different cases, then that's probably not the most efficient proof technique. But when you have 2 cases, it's not too bad. So let's get this one. So if we have x is odd, then that would tell us that x is equal to what?
2a plus 1.
Okay.
And then when we plug 2a plus 1 in for x in x cubed minus x.
And
do you want me
how
to
about
walk you
you
through all the steps of that? Or?
Cut to the chase here. I'll skip some of the algebra. So when you simplified this, what did you wind up getting?
Well, so when we got 8a cubed plus 12a squared plus 4a, and then we pulled the 2 out of there in order to get our 2 times an integer.
Yeah, so this is what you got after you simplified everything?
Yeah.
So what's important here are those ones cancel out. That's kind of the real key. That's right. And so now this can be written as
2 times
4a cubed, 6a squared. I guess you could factor in a, and then we've got 2a over here.
And then because 4a cubed plus 6a squared plus 2a is an integer, 2 times that is an even integer. Proving that when we plug x of an odd number in for x cubed minus x, we get an even number.
Yep. Good. Yeah. And so now you could show that we said no matter what the value of x is for any integer x, we see that x cubed minus x is even.
Yep.
Okay, good. Any questions or alternate ways of doing this by any of the groups? Okay, so then the last one is question 9. So the group who was doing that one, do you mind walking us through that proof?
Okay, yeah, I'll walk it through.
Okay, thank you, Stephanie.
So for 9, it was if f of x and g of x are linear functions, then f of x times g of x is a quadratic function. So p is f of x and g of x are linear. And q is that f of x times g of x is quadratic. So supposing that f of x and g of x are linear, you can write it out as like just regular like linear. So mx plus b, And you can do g of x is nx plus c.
And it might just be good to indicate what types of values are m and b and n and c. So if this is linear, then what do we know about the value of m?
What the, like it's an integer?
It doesn't need to be an integer. It could be like pi or, you know, some irrational number, but there's one value that it can't be. What number would, if I set m equal to it, is this thing no longer linear?
Oh, 0.
Yeah, so that, and that might be important. So here we're gonna let f be this and g be that. Okay, where we need to just be sure that we specify, since it's linear, it should have an x term in there. The b and the c don't need to be there, but they might be there. But we do want to specify that here, the leading coefficients are not going to be 0. Yeah. Okay, sorry, Stephanie. Back to you.
You're fine. So I guess if you don't want the b and c in there, that actually kind of makes it easier. So then when you just multiply those, it would just be,
Well, so to cover like the most general situation, b and c might be 0, they might not be 0. Let's leave them in there, right? Because in general, it might not be 0. So we want to make sure that we can prove this no matter what the values of b and c are. So yeah, so let's go ahead and say, well, what happens when I take f of g times, or f of x times g of x?
so then when you multiply it out, you get mn x squared plus mcx plus nbx plus bc. And in that, the highest, whatever order is the x squared. And since x squared is the definition of quadratic, then we know that f of x times g of x is quadratic.
Yeah, and I think this is important over here because you do want to, we do need to say that that coefficient in front of x squared can't be 0, right? As long as that's not 0, then we get a quadratic thing. If that actually winds up being 0, then we actually wouldn't have a quadratic. So this is where this claim about m and n being non-zero is going to be important. So since we know that both of those were not 0, then we can say m times n is not 0. So the highest power in f times g is x squared. All right, and that would give us f of x times g of x is quadratic. Okay, great, thank you. Any questions? So this definitely takes practice proving things. I don't think, you know, going through a couple of them together might not be enough. So feel free to practice some of the suggested problems. So in Canvas, there's a page called Additional Practice Problems. And if you go there, I suggested some additional problems from the textbook that would be good to practice. So give that a shot. There's a couple on the sheet that we haven't got to. And so kind of coming back to the original problems. I think we've done most of them. I'll just leave these more practice problems untouched, and I'll put the solutions up if you want to practice them and check them. But I'll leave that for you to work on outside of class. Any other questions about direct proof? Is it starting to get a little familiar?
I have a kind of a question.
Yeah, sure.
some of the proofs have like, I want to say like tricks to them that like are just things that you have to practice over and over again. When you like when you post the answer key to like a sheet like this, will you also like say that like this is a common proof or this is like a commonly used theorem, or if that makes sense? I don't know if that makes sense or not.
Yeah, I mean, when there are certain things that are I mean, I think the only thing that really came up here that I think might have universal appeal is the fact that this proof of cases is a very common sort of thing. I don't know. I feel a little. I don't want to give too much editorial comment on these things because I don't know. They're all kind of different, but I do try to like say, okay, here's something that they all have in common is something like this, and along with the cases. But I think outside of these couple of points, it's a little bit, you know, depends on the different part of the problem. So I can certainly try and summarize like what's the big picture that is going to apply to all of these sorts of problems. And I think that for this, for these exercises, it would have been this part right here. Yeah.
Okay, thank you.
Okay, so then if there aren't any other questions about this, let me just introduce a couple of things on the next worksheet, and then the rest of the worksheet is going to be essentially what's going to be on your reading quiz for Monday. So this is the worksheet 5 dealing with introduction to sets. And so some of these things I actually asked you some questions about on today's quiz. In particular, like these common sets of numbers. So we're in chapter 1 in case you're curious about where these materials are. We can spend a whole semester just talking about set theory. So that's not the goal, but the goal here is to just get some familiarity with the notation for sets and some operations that we do with sets. So a set is a collection of elements. Sometimes we just write every single element in there. Oftentimes we're dealing with sets that we could describe in more general terms. So if you're kind of thinking, well, which is like a more elegant way to state set A, this would probably be preferable as opposed to just listing all of the elements out. These are actually not the same. Now they are. Cat's getting hungry, sorry. Okay. And then otherwise, we've been using this in notation, and just be aware that when we put a slash through it, just like the not equal sign, it means not an element of A. So that's this one over here. That's how you would read that. And then we've got our common sets of numbers. And the one that I didn't ask you about on the quiz because it doesn't contain any numbers is what's called the empty set. So the empty set is the set of nothing. And we denote that with 0 with a diagonal slash through it. Okay, otherwise we got natural numbers, integers, rational numbers, real numbers, complex numbers. So some fairly straightforward questions about these number systems. So you can give me like a thumbs up, meaning true, thumbs down, meaning false. 7 is an element of Z. Yay or nay? Very clearly, that is an integer, so that is true. 3 minus 3 is in the natural numbers. No, that is false. Right. Okay, 1 is an element of the empty set. that is false, right? There is nothing that's in the empty set. If we said 1 is not in the empty set, that would be true. Pi is in element is in Q. True or false? Yeah, that is definitely an irrational number. So this is false, right? Square root -1 in R. Thumbs down on that one. So the square root of -1, right? That's what we define as the imaginary number I. So this doesn't make sense in the world of real numbers, but it does make sense in the world of complex numbers. Sorry, I think I cut somebody off.
Isn't it saying not in the set of real
Oh,
numbers?
it says not in the set.
Yeah.
See it? Very good. Wilfred, I was just making sure you were paying attention. Good. This is true. I is not in the real numbers. Thank you. 1 plus 3i, is that a complex number? That is a complex number. Good. Okay, and so on. So I guess we shouldn't just stop. So in 7, what do you guys think about that one? So if it's not clear, right, what this set is saying is it's saying this set consists of all integers such that 7y squared plus 9y plus 2 is equal to 0. Does that seem true or false, that 3.5 would be in there?
Be false.
Why is that?
Just don't think the math works out.
The math does work out, oddly. If you plug 3.5 into that equation, I believe you get 0. I think that it checks out. Maybe not, but there's even a more glaring issue here, regardless of whether that works or not, which is what?
.5 isn't an integer.
That's right. So regardless of whether it works in that equation or not, this is false, since there's 2 things that need to be true. It should be an integer and it should satisfy that equation. So this is false, since 3.5 is not in the integers. And I believe if you do check the math here, that this should work. And now we're saying 3.5, that is a rational number, so that would fit into that set. Okay, any questions? So what your reading quiz is going to be about, will be about these ideas. So there are certain operations that we can do with sets, and the main ones are taking a union, an intersection, or a difference of 2 different sets. For the reading quiz, I'll pick some of these out to put on the reading quiz, and I'll make a video that works, that does some of these, and the ones that I don't do, I'll leave for you guys to answer on the reading quiz. Okay, so I wasn't sure how far we were going to get, so I don't have that quiz yet. Sorry if you're like really itching to take a quiz right after class, but I will get that up tomorrow. So in the meantime, definitely start working on homework 2 if you haven't already. And if you have any questions, I'll be around tomorrow for office hours. Just let me know. Otherwise, thank you, everybody. Nice to see everyone. Have a good afternoon. And yeah, if I don't see you, have a nice weekend.
Thank you.
And if you have some questions, you're welcome to stick around. I'll be here. Bye, everyone.